Welcome back. So the general approach to solving this aliasing issue, or at least improving it, is texture filtering. Now texture filtering is a huge category of techniques, and we're only going to cover the basics here, but this is pretty much what you'll find in run-of-the-mill systems, okay? The idea behind texture filtering, it comes from image processing, which is kind of beyond the scope of this course, but we look beyond the basic texel that maps to our pixel. So we look beyond a single texel to calculate our pixel color, okay? So here's an example. You could imagine we have, this is our texture here. I'm going to draw a little more roughly, it doesn't really matter. This is our texture. And what we're doing is we're mapping this onto some triangle. Now imagine we have this case here where we have our minification going on. Okay, previously we'd map that to a single texel, the nearest neighbor one, the best one. We'd fit that and we say that's our pixel. That's our pixel color. But with filtering, we basically look around that pixel. We go, hey, what are your neighbors like? And we take some kind of average. And that way we incorporate not just the one pixel, we incorporate the neighborhood. So as you change size and it jitters back and forth, it'll actually average back and forth, and you'll get a nice blend of color instead of those shimmering, those sudden jumps. So here's how this works. The first basic one, the basic filter you can set if you use a graphics engine, is called nearest neighbor. And unfortunately, it's not very good. It's what we've already been learning. No filtering at all. This is what we've already learned. You just grab the pixel and you're done. The texel and you're done. But perhaps the more common one is called bilinear. Now, I'm going to mention that there's a linear as well that we're not going to go into. It's more of a one-dimensional thing. But unfortunately, many graphic systems will say, turn on linear filtering. When they mean bilinear, it's a mess, okay? OpenGL calls it linear, probably because it generalizes to 1D textures and other D textures, but it's bilinear. And what bilinear does is it takes the four nearest texels to the one that you've mapped to, your nearest neighbor, and it interpolates between them. So it's a really simple idea. So this is how it works. So you imagine I have found my four nearest texels. And let's say I have this point, I shouldn't use red. We have this point here that I map to. And of course this is from my raster, right? I have a pixel here, and this maps to this point here. I get the four nearest texels, okay? Now what I do is, it's called bilinear because you do two linear systems. First, I go, okay, let's average between this pixel and this pixel, make it a line, and I'm going to average it at this spot. And I'm going to do the same between these two and average at this spot. So I get these two lines, and I interpolate them and find the average at that coordinate. Then what I do is I turn sideways, and I go this way, and I go, aha, that's where my pixel is. Aha. So I first interpolate these two pixels that way to get a result on each side. Then I interpolate between those two results to get my final pixel value. That's it. That is bilinear. I take four pixels, I average in one dimension, find at the interpolate at the pixel mapping location where it is, and then I draw a line across and I find the other coordinate. So y coordinate here, and then I go x. Doesn't matter what order you do them in. Cool. And this actually works quite well for this is a minification example. This actually works quite well for magnification too. Okay. So you can imagine where I'll have a similar texture where I'm trying to map it to an image scene, but now because of magnification it's bigger. Now imagine I have this pixel I'm trying to shade. Previously, again, I'd map it to this spot here, and I'm going to pick a spot, right? Aha, that's my mapping. Previously we'd take that and then many pixels would map to the same text and we just take it. But because of this bilinear filtering, we end up taking the neighborhood and interpolating across them. So a good way to think about this is imagine that you have the pure one texel there, one texel like that, and you're just smoothing between them, and you're smoothing between them in 2 dimensions using our trilinear filter. So each pixel that you fill in will not just be one texel than the next, it'll interpolate between them as you do that linear interpolation. So we've done lerping already. This is just lerping on pixels. So bilinear filtering sounds complicated. You do linear twice. I do linear between these pixels, and I filter them into lines, and then when I filter them and I find the interpolated spot, then I go between them and I end up at the color I should use. And as that spot moves, let's say your scene is moving and rotating, you'll get a nice smooth interpolation between those 4. So bilinear filtering is great. It's very common. You're going to use it. You're going to see it. But slide 29, I didn't skip, right? No. But it does break down. So let me explain the edge case of where, not the edge case, the end case of where it doesn't work. So bilinear filtering is great, but it breaks down when you have too much minification. Okay, and you can think about it because what I'm doing is I'm taking a 2x2 sample area of my texture and I'm averaging it in there. But what if this 2x2 sample area is too small? What if it's less than 1 pixel size, right? So imagine, you can imagine where I have something like this, and this is my texture, and I'm going down to this really small spot, and so in here I have this one little pixel, and I come out here and I do a 2x2 mapping, but this space is smaller than the pixel. This 2x2 patch, we call it, is smaller than 1 pixel. So in that case, we're back to where we started. We get this aliasing problem all over again, okay? So again, you can imagine this 2x2 sample area is too small. This here, right here, if it's smaller than 1 pixel, we're back to where we started. The solution, of course, is using a larger sample window. So instead of looking at a 2x2, you could imagine looking at a 4x4 or whatever you want to be bigger than that pixel. The problem with that is it gets expensive very fast, n squared. So it's not directly, at least, an approach we want to use. There's a lot of other ways to do it. So let's go over to the slides. So here's an example. Now, keep in mind that people look at this and go, it still looks pretty crappy. Yeah, we still have limited resolution, right? That's kind of the idea. What do we do when we don't have enough resolution? If we do nearest neighbor of this kitten, you see it looks blocky and chunky, right? But if we do linear interpolation, it looks a lot more smooth. And so when it's moving through a scene, it'll look a lot better and a lot more natural than this blockiness that we get. Here's another example of nearest versus bilinear. Now, this is a nice example because at first glance they look kind of the same, right? But if you look closely up front, these jaggies here, and maybe I can zoom in, ooh, that's kind of trippy. The jaggies here, they go away and they start to smooth out nicely, and the whole thing, especially at this middle region here, looks quite a bit nicer. And again, this is meant to be low resolution. We're zoomed in. If you have a high-res display, it wouldn't look so blurred. It would look soft and nice. But as we go into the scene, we're back to where we started, right? We have this aliasing problem. We didn't fix it because our patch isn't big enough. It's not sufficient. All right. So I'm going to take a break there. We'll stop, and I'm going to come back, and we'll learn about a technique that we use to fix this without having to have these very big expensive patches.